second lecture of the afternoon is by Andras Szenes, who will speak about deformation quantization of moduli spaces of flat connections on Riemann surface.
Hey, Riemann surface. Thank you very much. I think it's an honor to be here and speak today in front of you. I made somewhat a peculiar choice for the presentation because this is a work that I did 25 years ago, actually, so this is not very new. On the other hand, there is an absolutely miraculous coincidence because, in fact, I could have given the title to this talk could have been exactly the title of the next talk that you're going to be listening to, which is the what was it called? The non-perturbative deformation quantization. This is about non-perturbative deformation quantization. But I didn't know that Maxim talk was going to be about that. Is just by coincidence. It's exactly the same topic, and it's not quite a coincidence because the story of this paper from 1999 is that it's probably I was never quite as excited about a piece of mathematical work as I was about Maxim's paper on quantizing Poisson structures, and so I was just running around with it all over the place in Boston. In fact, I gave probably about like 15 lectures on it, and you can be sure, I'm almost certain that if anybody heard about this in Boston, it was from me. Even Kashdan heard this about from me. So I was very, very excited, and so eventually, once I understood what I could understand, and I thought how I could apply this, and so my subject is topology of moduli spaces, mostly moduli spaces of flat connections on Riemann surfaces or stable bundles or other bundles on curves. And so I try to apply try to apply deformations or deformation quantizations to this to topology of moduli spaces, and this is what came out of it. And I'm very proud of this piece of work. It's not conclusive, and so we finally ended up with a conjecture, with which I'll finish the talk. And this conjecture, as far as I know, is still open, but its status changed over time, and there's a dynamic of conjectures. And so that's one reason I'm giving this talk, because now it's in a different place than it was before. So lots of things have happened since derived geometry, a lot of advances in cluster algebra, which are all relevant to this subject. And I think that now this is much closer. So when I talk about the dynamics of the conjecture, what I mean is that that at the beginning, like in 2000, when I asked people about this, I said I have no idea about how to approach this. And then it slowly changed, and about 10 years ago, things changed, and people started saying that it's trivial, the conjecture. So it's obvious. And then they disappeared for 6 months, and then never came back. And it's repeated several times. So I think now this conjecture could be solved. And many people think it can be solved, but I think it's still open. So, and I think this is one of the, in a sense, I think it's a centerpiece in some ways of this subject of exactly non-perturbative. It's a non-perturbative example of deformation quantization. Okay, so let me explain now what this is. And now maybe it's not very complicated. It works. So this is my subject, mostly moduli space of flat connections or Riemann surfaces. So we look at the, it promised me a laser. This little thing, you see? Okay, it's there. So the Riemann surface, I take the puncture case, that's the simplest one. Of course, then this is already an error, so that's why I want to be like that. So of course, it's form of I1 of the puncture Riemann surface with values in some say, compact or non-compact group, and then you divide by the adjoint action. That's the moduli space of flat connections, and we are interested in the topology of this space. And so then, I will, as usual, I will take a conjugacy class of the group. So I will mostly, and in fact, our work really conclusive only mostly for SU2, for rank 2. In that case, so then the conjugacy classes can be parameterized by I'll take non-degenerate conjugacy classes by some real number between 0 and 1/2. And but in general, for now, we take an ML conjugacy class, and then we can look at the moduli space now with restricted holonomy along that point. So I look at MX now, which is just those flat connections on the puncture Riemann surface whose whose holonomy around the point P is in this conjugacy class. Okay, so that's now the one advantage of that is the following: is that in fact this original space is a Poisson manifold, and these pieces there are leaves of that Poisson manifold, which are symplectic, and so they have a natural symplectic form. And in fact, say for SU2, all these spaces, in fact, they are holomorphic. Oh, sorry. All these spaces are diffeomorphic to each other, in fact, so there is no topology change, but there is a change in the natural symplectic form that comes with it. It's basically it's a linear function in the space of symplectic.
Question. What is the Poisson manifold?
Oh, the original one, the MG.
Also, you said there is a Poisson structure.
That's why I said this is the Poisson manifold, and these are the leaves.
I see.
Okay. Yeah. So I said a Poisson manifold. That was a mistake. Yes, sorry. You're right. It's this Poisson manifold. Okay. Yeah. So that's sort of the basic setup, but we're still interested in the topology of these spaces, and so now there, as if you know me, you're not going to be surprised that I was very interested in this particular quantity. So you look at the A hat, basically the Euler characteristics of this bundle, but with the shifted thing. So you look at the e to the kx, k is just some parameter, this omega x, which you see here, the symplectic form, and then you have this the A hat genus, which, for example, for the rank 2 case will not change with that. So this is basically, and roughly you have essentially have two parameters in this form, right? You have this k and this x, and this is basically a polynomial, an integral. It's an integral over mx. Yes, it's the integral on this space. It's a Riemann-Roch theorem essentially on this symplectic manifold, and the result should be some polynomial into there. So roughly, I can even tell you what it is in the rank 2 case. It's not very complicated. Again, it's a polynomial in x and k, and I like to give it in this kind of residue form in a third variable u, right? exu exponential, and then you take 1 minus 2 times hyperbolic sign of this. It's roughly it's this. So that's it should be something else. So you can write it down explicitly for rank 2. For higher rank, the formulas are a bit more complicated, but let's just focus today on rank 2. So roughly, the purpose, the idea is to use deformation quantization to reproduce this formula. This is what we are trying to do. So, so let's talk about deformation quantization. So, formal. This somehow is called formal deformation and traces. So so deformation quantization is some non-commutative thing. So I take M, some arbitrary manifold, and on the smooth function C on manifold, I have the old product, which I just write FG. That's the old commutative product, and then you have a new product, which is F star or dot G. I didn't dare to throw a star. F dot G, which has this property of you can write it. So it's this locality. which is, yeah, sorry. So the deformation parameter, if I didn't make a mistake, I hope I've changed it everywhere, is t here. On my paper was it h. So it's t to the n, it's a power series, and this VNFG is just some bidifferential operator that that results in a function that that you apply to FG. And of course, the key thing, and this is that you want this to be associative. I mean, that's the whole point. So you define these operators in such a way that the thing is associative. And this gives you an infinite number of completely intractable, well, it was intractable until Maxim's work, intractable equations, which he solved spectacularly. So I will not talk about that. I will mostly concentrate on the simpler case of a symplectic situation. But in any case, one thing that's easy to check, I think this is called Drinfeld's lemma. I don't know if it's true, but the fact is that if you take the commutator of the first element here, B1FG, as B1GF, then this is a Poisson structure on the manifold. As I said, we'll be interested in the case when this Poisson structure is actually symplectic. So a simple example is the Moyal product. So that's a non-compact case. I mean, most I'll be interested in compact case, but here it's a non-compact one. I look at R to the 2n, and it's an explicit, completely explicit formula for this, which is that you look at the basic, you take a symplectic form, and as a standard symplectic form R to n, and you take the corresponding bivector field as a bilinear operator, and then you take its exponential with this parameter t, apply it to f tensor g, and at the end, this m means just that you multiply the result of the multiplication. Okay, so this is a fantastic solution, actually. It looks simple, but actually it's a fantastic solution to this thing. It's a nice exercise to check it's associative. It's not completely obvious. And so this actually a standard deformation of this symplectic structure on R to n. Okay. Now, what we'll be interested in, why I'm also giving you this example, is the idea of traces. So there's some, I'll explain this later. We will be interested in the notion of trace. So the trace is just the usual thing. So I take one of these things, FG, one of these star products, so these new products, and it's non-commutative. And so we're interested in sort of linear functionals, which are zero and commutative. So I'll call a trace is simply something that satisfies this blue thing here. Trace FG, sorry, no, this is a mistake. So F dot, it should be F dot G, so the trace G dot F. So with this non-commutative product, obviously, you want, I will be interested in traces. So traces are linear functionals on this new product algebra, non-commutative structure. So we'll talk about that for a second. So what are these traces? So now here, that's why this thing appeared here. So you can think of this as a family of algebras, right? Depending on T. Well, it's a formal family of algebras. In any case, this trace is just, depends, of course, on this algebra structure, trace FG equals straight J. Okay, so this one is zero on the commutator in this algebra. Okay. Now, well, it's canonical. This is a subtle issue. Maybe I won't explain exactly, but there's a canonicalness in this choice. So here's the definition of the canonical trace. It's called Frey-Moyal F. And the form is, again, remarkably simple, but it's not completely trivial. Is the fact that if you take, well, here it's a compactly supported function f, then the integral of integral of f is a trace. So in a normalization here, it's not so. Okay, so the integral is actually a trace. Of course, in general, for the general product, this is not really true. But for this particular thing here, this is true. So when I would say that this is a canonical trace, so well, the idea is that you can perform some automorphisms of the algebra, and this trace remains invariant under automorphism. So actually, this includes this formula here, and this is absolutely crucial, firstly, includes a normalization of the trace. Okay, so of course, when I talk about traces here, Obviously, if you find one trace, you can multiply by t to the n, say, and you get another trace. You can multiply by 15, you get another trace. So there's a normalization. So there's an sort of a, essentially, there is an you can any trace you can multiply by a t-dependent constant. So there's lots of them. And in fact, I wrote it somewhere later on the slide that in fact, for a symplectic manifold, actually there's a unique trace up to this normalization. But the normalization has an infinite number of constants, right? At any power series in T. So what's happening here is that this formula, at least for the Moyal product for now, it fixes this normalization to be just the integral.
In case of general definition, how does these ENs depend on n? In general.
What do you mean how? It's a set of equations, and we don't know. They don't depend, but they have satisfied relation which comes from associativity. The only relation, I mean, sorry, so I didn't maybe write it here, I assume it. So the idea is that a formal deformation is a formula like this, where you assume associativity. So now if you assume that Bn are some differential operators, which is part of that, then you get, it's just like millions of relations, non-linear relations, a set of non-linear relations. And yeah. And it's the essence of associativity in a sense. I mean, if you want to understand what associative is, you write down a bunch of relations, that's what you get. In particular, you write down what associative is for B1, the first one, then what I said is here, what it means is that if you assume associativity and apply it to this B1, then the actual statement that you get is that B1 FG is a Poisson structure. That's kind of remarkable. Oh, sorry, no, the outcome B1 FG minus B1 GM is a Poisson structure. It's kind of remarkable. So it's, yeah, sorry. So I didn't go give an actual honest introduction to start on. So that's the thing. So yeah, so once again, maybe I repeat. So the star product is just a sequence of these BNs such that this thing now it satisfies associativity. And that's just like millions of nonlinear functions. Okay, but so I will assume you already have one. And the existence of this was actually proved earlier for symplectic manifolds and by Maxim for Poisson manifolds in general. But in any case, get back to here. Once you have one, say for a symplectic manifold, you can classify the traces. They are all multiples by power series in T of a single one. And this single one can be normalized. And now the point is, the following is that, well, it can be normalized for the Moyal product, this particular one, but it turns out that locally, because of Darboux theorem, essentially, every star product looks like this Moyal product. And so this particular integral here in a somewhat convoluted manner fixes the normalization of the trace for any manifold. So the upshot is, if you don't want to follow it, is the following, is that for any symplectic manifold, and any star product, let's call this or formal deformation star product, something, formal deformation of this sort, you have a unique trace, which is called the canonical trace, which is normalization in some convoluted manner is fixed by this integral formula. Unless it's convoluted, because of course locally it won't look necessarily like this formula, right? When you take the local coordinates first, you have to convert it, you do some other morphism. So, but finally, once you've done that, it will actually normalize it. It's in every concrete way, it's probably an impossible amount of work to actually find this normalization, and that's one of the issues here. But theoretically, it's true. There's a canonical trace there. And this canonical trace, now I want to make one more comment of a similar kind, and it's the following. So again, the way to, so I hope it's here. So the way to think about, there's another kind of way to think about this, is kind of the right way to think about a star product of formal deformation, and it's the following, that instead of saying that I take a new product on the functions of a manifold, I'll just say that I take this A0, this commutative algebra, which is the functions of the manifold. So A0 is just this commutative product here. Then, and now I construct a family of algebras over the formal family of algebras. And then I also construct what I call a section. So this gamma, which goes from A0 to AT, and so I assume that this AT, this is a flat formal family of A star. And this gamma is a section. So that data is the same as this. What's important is that this section actually is kind of superfluous, and this is the whole mystery of this subject. So it really, this trace, even though you see now I do this convoluted thing, which seemed to have to do something with the manifold, right? That I take a local chart on the manifold, and then it looks like something. In reality, this normalization point does not depend on the manifold. It's some intrinsic property incomprehensible to me. Actually, property of the algebra itself. Okay, so in principle, what this says is that if you take a certain types of algebras, they have some canonically normalized traces. I mean, the sort of the mystery of the subject is how to understand it purely from the point of view of this algebra. That's not hopefully. The only way I know how to do it is to identify, take a section like this, choose one, think of it as a module, a space functions on a manifold, take a local chart, find an isomorphism with the Moyal, and then see how many times the integral you get. That's the normalization. But there's no direct way to get from AT to this thing.
Right.
Well, you will obviously explain how it's done, but I don't know. Okay, so that for me that's the mystery. Yeah, no, obviously some people know, but I don't. Yes, so that's the.
No, I can actually say that you have periodic cyclic homology, yeah, and periodic cyclic homology get a flat connection, gets a connection, yeah. But then it has also Hodge filtration. With this family of algebra, it's covariantly constant. And when consider associative gradient, you get Hodge homology.
Okay.
And then you get canonical identification of Hodge homology of this algebra. So
Okay, but so does that actually do it for you? So explain I mean conceptually what it is.
it's conceptually, yeah.
What it is. Then actually to get it,
Yeah.
we can actually get the into. So this they get. No, I understood what is it, but you actually get the, which one is the integral.
It's kind of
So
a fundamental class of a manifold, actually. You essentially do identify this as homology of manifold.
Okay, so anyway, so that's actually why I kind of bring the focus. I wanted to know finally where. Okay, so it's not a very easy thing to do. In any case, indeed, you want an algebraic device to do this, and this is sort of what was get by myself. Okay, well, let's just assume that's my thought. Okay, now, so now the point is how, if you remember now, maybe just I wanted to get to this thing. I want to reproduce this thing. So and so the idea is is the following, that so I am here now with this normalized trace and this deformation. So I'm here, and now this is a new part. So the point is another thing which is also which was known earlier, and actually Fedosov's work was not done much. It was a few years before Maxim's, but he solved this for the symplectic manifold case. Is a classification up to isomorphism of these star products, and so the classification is that for each of these star products, there is a characteristic class, which is omega over T. So omega is the symplectic structure, at times some power series with values in the second cohomology of the manifold. So basically it's some two cohomology class, but again, with infinitely many parameters. Okay. And so then there's the Fedosov-Szenes index theorem, which says the following. So this is this remarkable thing that I like very much, is that in this whole set of finding, I have two objects. And both of these, by the way, this canonical thing and this class also only depends on this family of algebras, not really on this section. So you just see this have sort of a flat family of algebras deforming, if you like, deforming the commutative algebra of function and manifold. Then what is true is that if you just take a function 1, which is fixed, so that's flat fixed, take the canonical trace, in principle, you get a power series in T or a Laurent series, the way I normalized it. Then what you should get is the exponential of this characteristic class, and then multiply by the A hat genus of the manifold. Let's just call it index theorem in deformation quantization. So there's an obvious analogy between this index theorem, the parallel Fedosov second index theorem, and the usual index theorem, which calculates sort of Euler characteristics of line bars. So the idea then, it appeared that what one could try to do is just to kind of reproduce this thing. So find the deformation, so a family of algebras, and calculate the canonical trace and calculate the characteristic class, and then what could compare these two things. And in principle, you could, if you could know this thing and this thing, then this would actually explain how to integrate, how to the Riemann-Roch calculus on the manifold would come out of it. So so it would seem like you could do the following thing. You could take a manifold, you could take its formal, you could take a formal deformation. If you can calculate the canonical trace and this thing, then in principle, this completely explains what the Riemann-Roch calculus of the manifold is. And formally, it looks like you'll be doing something, but so maybe now, as explained, maybe it's not so different, but it looks from outside that you'll be doing something very different. I mean, here it's usually, I don't know, localization, you do various, you calculate the integrals of characteristic class and the manifold is one thing, but here you simply, deform multiplication and then look traces and try to normalize them. So it's kind of a different type of work. So I wanted to compare this thing. And I made some headways doing this thing. So that's what I'll explain. So let's first, how do you deform the moduli space that I defined at the beginning? You have the moduli space of flat connections. And so it's essentially, so we found, I think, a very kind of cute sort of a way of presenting it, but this is something that was essentially known. This is essentially the definition of the Riemann-derived invariants, but presented in a slightly different way, so that it actually creates a product of this family of algebras. And so I will not explain that in detail, that would take forever, but I'm just roughly give you an idea what the objects look like. So this sigma here, you see this sigma here, the black thing here in the middle, that's a slice of the Riemann surface, and you thicken it, so you take sigma plus epsilon and sigma minus epsilon. So you thicken the space, and now I will define an algebra FQ, but I won't really define it because that would take a little while. I would need to explain all the derived kind of yoga for this, but it roughly looks as follows. You both below, this is the red thing, inside the surface, and outside the surface, that's the blue thing and the red one. Exactly. You define you take some graphs which are enhanced with some on each line. These are ribbon graphs with some representations and invariants of a quantum group on the vertices, etc. So this is some object like this. And then you can take unions of these, and then the product, that's sort of visually the only thing that needs to understand, is simply taking the union of the two graphs. One is below and one is above the surface. And the non-commutative comes with then you cannot topologically pass one graph from the other ones. You cannot exchange non-commutativity of the things. That's this BA. So I won't explain more about this. A little bit about, and then what happens is, of course, you get something too big. So you want some relations. So this blue thing now is above the red thing, as you can see. And then the relations are roughly have to do, if you exchange, you want to pass one to the other, you have to apply the R matrix, roughly. Exactly something of this. Okay, so you have, and then you have some other relations, which we completely described, and so it's you can actually verify the flatness of this algebra using this technique. So the key thing that will be important for us, that there are some sort of these cute little central elements of this algebra. So remember this, sorry, I didn't put this here, this dot, of course, is the point P. So now you look at the ribbon graph, and you have some Lie group, say SU2, and lambda is a weight of this group as dominant weight. So you basically just take a circle, a ribbon here with this dominant weight in there. But one thing that's easy to understand that these elements are central in this algebra, because of course, if you are here around this point, you can easily pass this ring past another more complicated graph, right? So two things can, if it's just around here, it can be easily passed one past the other. Okay, so these are central elements. And then you define a quotient algebra, which is that this algebra, where you set the values of the C lambda to be a number, which will be the corresponding character of the group evaluated at this X, which is, you remember, was the conjugacy class. So a character can be evaluated conjugacy class, and you just make this relation, and this gives you a quotient with respect to this central character, if you like, of this Brechetian derived type algebra divided by this ideal. Okay, and so this result, this FQMX, is now a non-perturbative deformation of the moduli space of flat connections on Riemann surface with a fixed monotron. Deformation, a Q deformation of a symplectic manifold.
It's kind of countable dimensional algebra. It's kind of
Right.
it's countable dimensional algebra. Yeah, countably dimensional.
Yeah. So of course, I'm cheating here a little bit. So
yeah, it's kind of like polynomial functions on
Yeah.
computation. Yeah.
Of course, the idea is that when you have a star product, you're kind of vaguely hoping that in order to measure these b's, it's enough to know a smaller. You don't need to know whole function.
Like, what's the dimension of this tubular neighborhood?
Dimension.
Oh, it's 3. It's in 3 space.
Three is-
Yeah. It's just you imagine that. That's why I do it. The surface, and you just got it outside and inside.
It's a sigma cross B.
Yes, it's sigma. Yeah, it's sigma cross an interval. Yes, but I thought if you imagine it in the space, it's easier. But yeah, it's sigma cross the interval, and it's black is 0, and then plus epsilon and minus epsilon. Okay, and you put on the outside, you put one ribbon graph, and inside another ribbon graph. And you cannot put them as each other, but if it is around the puncture, then of course you can. And usually that's clear, right?
So this M is compact or?
Yeah, surface is compact with this puncture. I mean, it's punctured. I don't know if you want that to be compact. It's kind of non-compact, but I mean. I mean, what I mean is that, well, it's non-compact in a sense. If you want to think about flat connections, then it's non-compact, or it's function. But,
You can make a pool. Then
you can also make a hole. Yeah.
you have a bubble.
Well, when you puncture, you get a hole. I mean, okay. So let me now just go to the. So of course, there's a lot of kind of calculations going into this. I'm not going to explain, but so let me now go to the trace. So I'm going to try to construct this canonical trace and this other thing. I'm trying to kind of converge now to the. So again, the purpose is roughly is this. I want to reproduce this thing. I want to find a canonical trace of 1 in the deformation, and then this class theta star. Okay, so I'm going towards the trace. So what I'm saying is the first is the following. Let's look at, so you have to just remember maybe this algebra. So you have this algebra is FQM, and then this FQMX is when you take FQM with these ribbon graphs, and then you divide by these relations. Okay, so these are the two things, FQM and FQMX. Okay, so now first I just will look at traces on FQM. So there, it turns out this dq is some meromorphic functions of the unit disk or something like that. Okay, it is dq, and it's some sort of projection onto 1. It's some very simple thing, really. I mean, I won't be able to explain it now in detail. It's kind of a cute little calculation, but the point is, it's easy to see that this is a trace. So it vanishes on commutative. This is HAB equals HBA, easy to see, and.
Sorry, Andras, can you say at least what you mean by 1? Like 1 as a function, 1 as a level in your thing, 1 as what? No,
1 is as a function. Yes, so on the algebra. So yeah, I mean, you're right. I mean, but like here, for example, there is a 1. Yeah, right in the algebra. Well, so certainly there's a 1 in the algebra function. That's clear. But now, yes. So No, I think, so I think one is when I take, so I think, so it's a little subtle actually, this is not important in fact, but it's, I think if I'm not mistaken, is that I have to take a graph that actually, as it spans the whole thing, and then, so a correct graph, which is, and there I take a trivial thing everywhere, so trivial representation and trivial invariant. So the dress, the representation on each edge and an invariant on each. And I think if you take trivial everywhere, you can make a projection onto that, something of that sort. So the one thing that's not so trivial, but it turns out it's true, is that, and this is exactly why it's relevant, so actually it's a very good question, is that if you take C lambda and you take its H, then you get this quantity here. Okay, and so this is not so obvious, but that's because the point is that the circular graph around it is not the kind of graph. No, so basically what you get is that you kind of push out this circle to the graph, and it will have 2g minus 2 kind of edges, you know, if you press it out to this graph, which is the correct one, which creates a cell, right? So whose graph whose complement is a cell. So the problem is that if you just pick a circle, its complement is not a cell, and so that's why this is not correct. So anyway, you have to just believe me, this I will not be able to explain now, but in any case, if you make the correct calculation, this is just some completely elementary thing, you get that this is the h of c lambda is q ding b lambda times 1 minus 2g.
So it's okay if you take a surface and then you take a torus. You take surface cross S1. You compute the variant of this graph in this surface.
I mean, you're invariant.
Yeah.
Yeah. So that's another way. Yeah. So it's related to that. Yeah. Yes, but so I didn't want to actually, yeah, actually there's right invariant. But so as I said, this is a relatively close thing. So anyway, so this is the calculation which I'm not going to explain, but that's the result. This is going to be easily calculated. Okay, so there is some trace H, which is easy to describe with this property. But of course, the point is that now there's millions of traces, and that's because this F, you remember, is to the deformation of the Poisson manifold. So it's not in here, and so in fact, for each lambda, you can take you can create a new trace by saying that H lambda F is H F C lambda, since C lambda was central. So this is also a trace. So there's millions of traces. You have basically for each lambda, you have a new trace. So you have an infinite number of traces. Okay, so now comes, actually, it's kind of a trivial remark, but this is the main thing. So what happens is now, okay, I have an infinite number of traces, and now I take a quotient algebra of this FQM, this FQMX, and I want to concoct from this H trace, whatever it is, a trace on this quotient algebra. And it's easy to see that there is only one choice, and it's given by this formula. Okay, this is this.
What is lambda permanent trace?
Yes.
I see. So the infinite sum, yeah.
It's an infinite sum. Sorry, yes. So lambda, yes. See, lambda, so like for SL2 is just n. It's an infinite sum. So it's easy, and this is what makes this actually kind of remarkable, is that there's only one way of doing this, and it's this. So you have to take this infinite sum. You take it's a linear combination of FC lambdas multiplied by chi lambda x, and of course maybe there's a bar here, and because of course C lambda has to be equal to chi lambda in the quotient. Okay, so this is an easy calculation in linear algebra, that if you want to for the trace to descend to be compatible with the ideal generated by C lambda equals chi lambda, you have to take this linear combination of these traces. So you get an infinite. So now you go into analysis somehow. You get an infinite series. Okay. But this infinite series, it turns out, so then we have to work very hard. You have to prove that this infinite series is still, it's a convergent holomorphic function in Q, etc., etc. So, you get something. I will give you the example. So, for example, you calculated, you get of course, the needed relation, which is this one. The trace FC lambda is trace F times pi lambda x. Okay, but let's just look at this one. So then you calculate what trace of 1 is, and you get this infinite series. Basically, it's
sorry, but you're confused. Because it's trace on the quotient algebra, yeah?
Yes.
It means that if you multiply things by C lambda, it will be an ideal to the zero in quotient algebra. F.
No,
Formula.
C lambda is equal to K lambda of X.
C lambda is equal to chi lambda. That's a relation.
C lambda is equal.
That's right.
Yeah.
This is the relation. That's kind of logical, right? If you want, you want the C lambda to be the character of it's the C lambda is kind of the monodrom, and you want to be the character one. Okay, so here we are, and this is an amazing formula. I have to say, this is absolutely fantastic. I mean, this thing is, of course, so this lambda is just an integer, basically n. Is also some quasi-Jacobi form, I think. I mean, there is millions of properties. But so one thing that's absolutely striking, and this is what, if you remember, I mean, so we have this Q now, and this is exactly about non-perturbative. The main remark, actually, the main outcome of our paper is a remark on non-perturbative deformation quantization, is that this thing looks actually kind of bad. The reason is that, of course, our plan was that we will take Q, right, as usual, and you make it to be e to the IH or e to the H or something like that to make the deformation. So what you are hoping for, I mean, what you're hoping for, and what I hope for at the beginning, is that this function is a holomorphic function in Q. That is actually true. And then I set Q to be IH, and then I'll expand H as a holomorphic function in Flower series, right? So again, I'll get to that, but Q equals e to the H or e to the IH, like that. But of course, if you look at this, it's very well, it's kind of some modular form. This is not holomorphic at Q equals 1. So, and not at all. I mean, not even close, nothing. Okay, so this doesn't look very good. It looks like, yeah, well, this is this non-perturbative. It's exactly, yeah, like quantum field theory kind of thing. Right. So actually, instead of what is going to happen is the following. Is that what is true, however, and what I proved is that what we proved, but then you have to prove for every function all of those Riemann graphs. It's kind of tiresome, but we did it for rank 2. Is that you have and you don't have these functions are not holomorphic in H when you make this substitution Q equals e to the I by H. That's not going to be holomorphic. It's just some horrible function. I mean, horrible. It's like a modular form at the cusp, roughly, or something like that. But they do have asymptotic expansions, which are Laurent polynomials, basically, as H goes to I0 plus. But it's essentially this thing. So Q goes to 1. So this is this limit. Okay. So as Q goes to 1, these functions are not holomorphic, of course, because I mean you can see they have kind of a pole at every root of unity kind of thing, and it looks terrible. But actually, they do miraculously have asymptotic expansions, and the asymptotic expansion, when you calculate it, actually is equal to e to the omega x over t. So this is supposed to be t times the a hat genus. So now let's just stop here for a second. So this is just a calculation. We calculated those limits. They are not holomorphic, but they have asymptotic expansions. And we calculated that this thing looks like the theorem I want to get, except I don't know it's a canonical trace, but I did calculate some natural trace. And that trace does look like e to the omega over the integral e to the omega t over the manifold. This equality, of course, is based on the fact that I know already what this quantity is, right? E to the omega over a hat. I calculate independently. I get some polynomial, and that polynomial coincides with the asymptotic expansion of this trace. Okay, so that's actually the theorem. But so this theorem, then to interpret where we are now in the program, finally, is the following thing: is that we take it's the following. So, of course, what this looks like is like the Fedosov-Nestigan index theorem with omega x being the characteristic class. So the characteristic class equals omega x, and with our favorite trace, but converted into this asymptotic expansion thing, is to be the canonical trace. Okay, so it looks like when passing to this asymptotic thing, it looks like yeah, it looks like the characteristic class of it should be somehow omega x, and the canonical truth should be this one. Certainly, this equation looks like this, and the corollary is basically that what we proved is that these two things are somehow equivalent. So that if I know that the characteristic class of theta is equal to omega x over t, that's kind of the simplest thing it can be, then in fact that canonical trace will be obtained by this very natural procedure in the reciprocal theory and then passing to asymptotic expansions. So this is basically what we proved. And of course, then the conjecture is that either of these and so both of these are true. And so we want to know that these are true. And so I don't know how to guess that is basically the conjecture. So again, to repeat, is that this non-perturbative deformation coming from Riemann theory descends somehow to an actual form of deformation whose Fedosov class is omega x over t, so the simplest possible one, and then whose canonical trace is obtained as the one that I described, but taking an asymptotic expansion. And this asymptotic expansion is exactly this quantum field theory or non-perturbative kind of effect that you cannot really expand things as you naively thought you holomorphically in this thing, but you have to take asymptotic expansions. And so the conjecture that I'm still hoping now will be somehow understood maybe very soon is the fact that both of these are true.